Welcome again. Let me try to quickly summarize what we did last time. We are talking about closed correlators. In AdS3, so in the SL2R, going to mean Witten model. And so that meant that we were studying objects of this kind. In particular, we're looking at 3-point functions, mostly, but let's say n-point functions, where the vertex operators depend on these quantities here. So J is the unflowed spin, so the spin before spectral flow. H is the spin after spectral flow, which is also the unflowed spin. H is the after spin after spectral flow, which is also the spacetime weight, the boundary CFT homomorphic weight. Omega is the spectral flow charge. X is the boundary insertion. And Z is the worldsheet insertion. Okay. So we started looking at these objects. We saw that there had a lot of that these objects have complicated OPs with the currents, and we saw that the main point is that there are also some important constraints on the theory, which in the papers by so they have complicated OPs. For omega larger than 0, with the current of the model, so JAZ. We saw that there are a number of constraints. Which in the papers by the original papers by Eberhardt and Gabardier and Gopakumar were denoted as local world identities. And we saw that these led in the end to recursion relations. For primary correlators, so if I just call this for simplicity HI, right? So just to have a quick name for this, so the correlator of a series of vertex operators with some weights HY, and everything else fixed, then these recursion relations read something like something times one of the weights, say I don't know, H1, where it's shifted by 1 unit down. It has to be some combination, let's call it alpha I, of things where the other weights are shifted by 1. Okay, upwards. So there's always only I didn't say this clearly, but there's always one that's shifted downwards, and then the others are shifted upwards or not shifted. Like this. Okay. And then I argued at the end that there are a number of important functions in this game, which are holomorphic covariance, which I denoted as gamma, which go from, if you want, Z space to X space. Which the idea is that they help solving these constraints because they, if you can find them, they behave near each of the zi's has xi, so near each of the worldsheet insertion points, they give you back the boundary insertion points, plus, and the next non-trivial order in the Taylor expansion is way up. It appears as an order set by the vector flow chart. Okay, and then there are higher order corrections, but the main point is that all the terms in between these two are zero. Okay. Fine. So this should happen for all I. So these holomorphic coloring maps are useful for deriving the constraints, for deriving the recursion relation. And then the final point that we made is that we might want to introduce another continuous variable, which we call y, which allows to recast the recursion relations as differential equations in a new variable y, where the relation between where the idea is that this basically is a conjugate to h, to the quantum number h, in the same sense as for unflowed operators, x is a conjugate variable to m. And the main definition that I didn't give last time between operators with these y variables and operators such as that I wrote here. I don't know, you can use the word basis, but it's not really a basis. Let's say the y basis and the h basis. So the main relation between the two is that if you have some operator bj h omega x of z, you can get it from the integral over the whole complex plane of y, and here it's a similar transform as in the x basis to m basis. It's just j plus k over 2 omega minus h minus 1. The same with the anthropomorphic sector, where this h bar can be different, and then some new vector which depends on x, y, and z. So this here is the new important object. And in terms of correlators of this guy, so now we're going to study correlators of this form. Correlators which are I equals 1 to n of vj I omega I x I y I. In terms of these guys, these recursion relations are going to look like differential equations. Okay? And why is that? It's because we already know that when you have an x here, the element, the action of the currents, so the current act as, so j plus the zero modes is just dx, the zero mode of j3 is x dx plus h, and the zero mode of j minus is x squared dx plus 2hx. That's the usual thing. But now the nice thing about this new object here is that there are new modes that act as differential operators. And these new modes are simply, again, j3 0 minus k over 2 omega, j plus plus omega, and j minus minus omega. So these are the zero modes of the tilde currents that we had before. So the currents in the spectrally flowed brane. Okay? And on this vertex operator, these act as the derivative with respect to y. y dy plus the unflowed spin and y squared dy plus 2y. Okay, so that's how these modes act on these objects here. And if you remember, what happened is that this mode before is the mode that took h to h plus 1, and this mode here in this for this object is the mode that takes h to h minus 1. Okay, so it's a tilde curve. So what I'm saying is I'm trading recursions from differential operator to differential operator. Okay, and that's how you solve the whole thing. Oh, but that's what you need to solve the whole thing. And so, for example, for 3-point functions, the solution for 3-point functions which satisfy some conditions, the more important one being that the sum of the winding charges, the spectral flow charges, is odd. Okay. Then we can show that in these conditions and at genus 0, so at first order in the topological expansion, there exists always a unique covering map, gamma of them, which satisfies these properties here. Okay, so that's true for only, let's say, quote unquote, half of the correlators, right? So only for when, so let's call them odd correlators. So these are the odd 3-point functions. In this case, the covering map always exists, and it takes a very simple form. It's well, the form of the actual map is sometimes a bit complicated, but you can derive it explicitly, and you can explicitly find what these coefficients are here. And those coefficients are just so if you take the 3 insertion points to be both on the boundary and the worldsheet to be at 0, 1, and infinity, then the coefficients of the covering map are just simple numbers, and they take the simple form, so just combinatorial numbers. So it's omega I plus omega I plus 1 plus omega I plus 2 minus 1 over 2. Yeah. Ah, let me take this down. Yes. Okay. It's a bit expensive. Okay. Okay. Yes. So this so if I define this guy here as, just to give it a name, as I don't know, omega plus plus plus, because I have plus omega I plus omega I plus 1 plus omega I plus 2, right? Again, I'm talking about 3-point functions. So this means that the coefficient A1 is going to have omega 1 plus omega 2 plus omega 3, and then the indices are understood mod 3. So this is cyclic. And then I just have similar numbers here. Not make a mistake. So this is omega minus plus plus, and then I have another combinatorial number which is omega minus plus minus and omega plus plus minus, and this is to the minus 1. Okay, but this is just a number, right? You give me the set of spectral flow charges, and I give you, and I can compute what the map is if they satisfy this condition here, plus some, plus being larger than 0, plus omega I being larger than 0. I can compute the map explicitly, I give you some functions in terms of hypergeometric functions, etc. But then I can just go and compute what the expansion about each of the insertion points is and tell you what this number, which is the important number, is, and that number takes a very simple form, combinatorial form, which is like, okay, fine. So how do you use it? Let me give an example and not solve the whole thing. So for an example, let me say I start with the function which has J1, H1, and winding 1, B, J2, H2, and winding 2, H1, Z1, and winding 1. So all of the windings being 1. Okay, so this is the kind of simplest example you can think under these conditions. And you can check what the recursion relation looks like. So for example, the recursion relation, in this case, looks something like this. It looks like, let me say that I define coefficients C plus minus I being, so this would be HI minus J over 2 I plus minus 1 minus I. These are just the coefficients that appear when you shift H to H plus 1 and H to H minus 1. Okay, so this is the action of the current. But again, they're just numbers. And so the recursion relation simply looks very simple. It looks like C1 minus for the correlator where you shift H1 minus 1 has to be something like this. So it's 2H2 x to 1. X to 1 is just xij in general. It's just xi minus xj. It looks like plus x to 1 squared derivative with respect to x1 over z1 2, or acting on the original correlator, plus x to 1 squared over z to 1 squared c plus 2 h2 plus 1, and then you get the same with 2 to 3. Okay, so this is how one of these recursion relations looks like. Okay, I have something where I shift the index down, and then I have something where I keep the same and have some coefficient with some differential operator in x in front, and then another one where I shift the index up. Okay. So this looks ugly to solve, but if you just rewrite this in terms of this operator, so you translate everything, so you take h basis to y basis, and also you fix x and z at 0, 1, and infinity, which makes it very simple because the dependence in x and in z is always fixed by the global order identities. Then this looks very simple. This just becomes something like.
Sorry, Nico, do you have three recursion relations or just
one? No, I have three, yeah. Then I have the same for.
Okay, understand.
I have the same for 1 to 2, 2 to 3. 1 to 3. Okay. Yeah, so I could have. It was a bit long to write I and J everywhere. I have one recursion relation for each vertex operator. In this case, they all look the same because they all have winding 1. Otherwise, they are different. So this relation looks much simpler when you use the global order identities to fix this to 0, 1, and infinity, and you go to the y basis. It just looks like this. So all of this acting on your correlator that depends on V1, omega 1, Y1, V2, Y2, omega 2, and V3, Y, omega 3, Y3. This has to be zero. Right, so this is the way it looks. And now you kind of trivially solve the problem because you have 3 of these recursion relations, and the solution is very simple to find. Just put it in Mathematica or whatever, and it gives you what the solution is as a function of the y's and the j's. Okay? So is the procedure more or less clear? Yeah.
What about the initial condition, something like that? It's a first order equation.
Yeah. So you know what happens at y equals. We know what happens at y equals 0 and y equals infinity. Y equals 0 corresponds to going to from your whole all the possible values of h. This corresponds to the correlator where h is 1 is the lowest possible value and 1 is the highest possible value depending on where you are in the lowest weight representation or in the highest weight representation. So you know what happens there. That's more or less simple. And when you do, you find the solution, and the solution is simply that this guy, etc. So sorry, this is 1, 1, and 1. And the solution is that this takes a very, very simple form. The simple form is it takes the following idea. The following form is just minus 2 j1, x2 minus 2 j2, x3 minus 2. There's here a normalization, which I'm not writing, which depends on the ji and the omega I, but not on the y's, right? And something is called x1 to 3 theta k over 2 minus k1 minus k3, where xi is simply yi minus 1 and x1 to 3 looks something like this. So it's 1 plus the sum of I equals 1 to 3 of y1 plus 1 over, sorry, yi plus 1, yi minus 1. Okay, this is the solution. And the solution is very nice. As it turns out, the normalization includes what you would expect, which is the unflowed 4.3. Actually, we get 15. That's a bit of a detail. But it's very nice because it tells you that this function here, which depended on all the h's, right? Now that dependency is encoded in the y variable, and it actually almost factorizes here up to this term there, and the unflowed spins, so the j's only really appear in the exponents. So the exponents are fixed, and you just have these factors here. Okay. Fine, and then this, depending on case by case, you can see what happens if you try to use the integral transform to go back to the h basis. And as you would expect, in this basis, the correlators look much uglier. They are written in terms of something called Lauricella hypergeometric functions, whatever. But this is a very simple form to write. This is the solution for the odd parity correlation. If you do it more generally, so this one you could have done by itself. more generally, if you use the existence of the covering map, I'm calling odd parity correlators those that satisfy that the sum of the omegas is odd. Then the solution is almost the same. You can write it in this way. Take the same form.
Sorry, parity is the sum of the omegas.
Yes.
Okay.
Yeah. It takes exactly the same form. But now the only thing you have to do is use the covering map data, which is basically at this level just the coefficient AI, which appears in the expansion, and that leads you to a solution which is just changing this. With those combinatorial coefficients that I had before. Yeah.
I have a question from the top. So if I do if I express the correlation functions in X space, it's going to be an only expression. I agree.
In H space, yeah.
In X space.
There's always an X here on the.
No, I mean the X in the sense that in insertions of the boundary coordinates.
Yeah, but there's an X on both sides. The only thing I'm changing the H label for a Y label, but it's here I'm not writing it because I set the X is to 0, 1, and infinity, but there's an X on both sides.
The C's that you have written, are those the OP coefficients? I mean, that's what I want. That's the data I'm looking for.
No, so what appears here, because this is more complicated. It contains the unflowed OPE coefficients. So
yes, but omega dependence coming in. That's
the omega dependence is first of all in the integration of this thing, right? Yeah. Because all of these AIs depend on the omega.
That's fine. So basically, to calculate the OPE coefficient, I have to do the inverse of that integral.
So I have to do the integral.
Yes.
That gives you these things called Lorentzian hypergeometric functions, and that's where the omega dependence comes in. So it's all contained in these AIs. So these AIs, which are AIs only of the omega i's, contain all omega I dependence.
Yeah, because that's the CFT data I should be interested in, right?
Exactly. Yes. I'm not doing the integral explicitly here.
Some well-known integral expression for
that. So yes, for these odd correlators, yes, these are called Lorentzian hypergeometrics or whatever.
And my second question is there any simplification for large omega? Like let's say I take one of the omegas to be large. Like
that's an interesting question. That's something that, in some way, Gavardiel and there was a recent paper of Gavardiel and Bob Knighton, I think, among them, among the authors, looking at these kind of things. I didn't try to do it in general. So if the 3 omegas are large, in principle, no. But if, for example, 2 are large and 1 is small.
Yeah, like some extreme omega ratio.
Yeah, so those kind of things, yeah, you get simplification. I don't have a generic form to show, but yes, I don't think it has been studied in general. But that's a good point, and that's because when you start looking at 4-point functions, right? If you have two that are very large and two that are very small, then in some sense this looks like a heavy light correlator, where because the h's depend on the omega, so if omega is very large, the boundary weight is very large.
Yeah.
This becomes a correlator where two of the operators are large, are heavy in a sense. Not the usual sense of heavy, because it still doesn't scale with the central charge. But anyway, are much heavier than the others, and so simplifications are bound to happen. But I don't think I have, and I don't think there is a more general statement to say right yet. It's an interesting thing to study. But this is really remarkable, because so before 2019 there was just no way of trying to think about this, right? It was just a case-by-case study. Malacena and Uri had done the case where these spectral flows were 1, 0, 0, then you can go case by case with the 1, 1, 0, 1, 1, 1, etc., etc. This is a very general formula. By going to this formalism, to this Y basis, it works for all of the odd parity correlators. Okay? And this is, at least for me, this is a beautiful result. Fine. Now, you can ask, before finishing with this part, you can ask what happens with even parity correlators.
Sorry, I have one more question. The differential equation that you have written.
Yeah.
So correlation functions in AdS3, they must satisfy this KZ equation. Does it boil down to KZ equation in the known cases? Like Malacena already talked about KZ equations.
No, it's more than that. So what you can show is that, so these are 3-point functions, there's no KZ equation. But for 4-point functions, what you can show is that, I was going to say, let me make a comment in 5 minutes, and I'll come back to that in a second. But it's related, but it's not that information exactly. For float 4-point functions, it's hard to compute exactly what the form of the KZ equation is, because of the presence of spectral flow, and because the usual derivation of the KZ equation relies very much on the usual OPEs between the current and the operator, on the affine prime. So you can ask what happens here. Here, on this selection of spectral flows, right? For example, if I have, 1, 1, 2, then you can show that there is no covering map which satisfies all of these properties that I'm asking. Okay? The question you could ask is, are these correlators even non-zero? No. So the question is, if this covering map helps me compute them, then maybe when it doesn't exist, then it could mean that the correlator is 0. And actually,
no physical reason.
No. So let me just say why. And actually, you could say that the answer is just no. But if the holographic CFT was a symmetric orbifold, so this just shows that the symmetric orbifold is not a symmetric orbifold. So this condition is true for symmetric orbifolds. Whenever you have, if you identify these omegas with the twisted sector, right? If you have an operator living in some twisted sector in some symmetric orbifold theory, then you can show that whenever there is no such covering map, the correlators are always 0. Okay, and actually this happens in the tensionless limit, because the tensionless limit of the theory is precisely the dual of the symmetric orbifold. So in general, the answer is no.
You want to say a little bit more about symmetric orbital CFT? Or?
Yeah, of course, yeah. That's about today. So I'll be a bit more.
Sorry.
But yeah, the question is quite on point. So there's in principle no reason to say that this doesn't exist. But if you wanted the symmetrical, the holographic theory to actually be a symmetrical ripple, this would have to happen, and it doesn't happen. Yes.
This covering map story, I mean, if I just assume that the boundary field theory is a symmetric product, I will exactly arrive at this result, right? I mean,
Exactly. Yes.
So somehow this is confusing, right?
It's not exactly this result. It's not this result. I'm going to show what the whole one in the reason what I finished it.
Result, but I mean, you can arrive at this result just assuming that the boundary field theory is a symmetric orbifold.
Which at this formula, you mean?
Yeah, that one, for example.
No, the only thing you can arrive at the conclusion that the correlator should exist only when there is a covering map, but actually the holographic correlators you have to really, so these are usually written in terms of this h, not this y variable. So you'd have to understand what this y variable means in the symmetric orbifold to write it in this way. And in general, for higher point functions, you can have things that depend. So here I fixed the z insertion points at 0, 1, infinity. In higher point functions, that's gonna depend on the other sets, right? For example, for the 4-point function, the cross ratio on the worldsheet. And to compare with the boundary correlator, you have to integrate over z. So there's one more operation in the middle. It's not true that for 3-point functions it's true, but for higher point functions it's not true that the worldsheet correlator is exactly the boundary correlator. You have to do that integral, right? Because string amplitude, you have to integrate over the insertion.
It's also true for like orbifolds. Like if I have symmetric orbifold on the boundary, I also have for 4-point functions. I also have to do one integral over the worldsheet, right? It's not.
No, how many integrals you have to do depends on many things.
No, so if I have a 4-point functions, I have to do one integral. For 5-point functions, I have to do 2 integrals. 3 of those integrals are fixed by 0, 1, and infinity.
Which integral are you talking about? The cross ratios? No, but the cross ratios are there. I don't need to integrate over them. The cross ratios in X are just variables in the correlator, and I need to integrate over them in the boundary theory.
You're talking about correlation function in the CFT.
Yes, in the worldsheet, yeah.
No, the boundary.
No, so let's say if I want to calculate the.
So let's say a 4-point function. This is here the worldsheet 4-point function is going to depend on the z cross ratio and on the x cross ratio.
Yes, right.
Z cross ratio is on the worldsheet. You have to integrate over it.
Exactly. That's what the integral I was talking about.
Yeah, that's true. Yeah, that's exactly. But the x cross ratio is the cross ratio on the boundary theory.
Yes.
That one is just it's part of what you want to compute. You don't have to integrate over it.
No, that's what I understand. I mean, okay, I think I'll come back to you later on because my question was not exactly that. Okay.
So maybe you can ask again if you want.
I mean, the question that what is confusing me is that where exactly you see that the boundary field theory is not a symmetric product.
Here now, for example, here, these correlators, the ones that don't have a covering map, are non-zero.
Yeah, but not at the level of the covering maps, right? And when you derive the 3-point or the 4-point functions.
No. Here, this formula, if I introduce a suitable y variable in the boundary theory, I could derive some formula like this. Yes.
Okay. Only when you analyze the OP coefficients, you see that some of the OP coefficients are zeros.
Yeah.
And that's where you conclude that whether it's symmetric.
So if it was a symmetric orbifold, all of these would be zero on their nose.
Okay.
Yeah.
That's where you see the difference between. Okay, that's what I think.
But you can also do it at. I mean, I'm talking about correlation functions. For general K, that's what you can also look at the spectrum. The spectrum is going to look for the long string sector like that of a symmetric orbifold, but for the short string sector, it won't.
Yeah.
So that's already there. You don't need to go to correlation functions to say that it's not a symmetric orbifold.
No, exactly, but I mean that's what I know. But I was trying to see from the correlation that is.
Yeah, so this is one very precise statement where you see that it's not a symmetric orbifold. Okay. And so the question is, how do you compute them? Because you don't have a covering map, you don't have a nice way of deriving these recursion relations or differential equations in the y-basis language. And the answer is that basically you can just use series identifications, use what I call the SL2R series identifications. which, if you remember, they relate operators like this. So they relate representations, if you want, with some j, and omega with operators with correlators with some j over 2 minus j, and omega plus or minus 1, depending on whether this is, I might get the signs wrong here, but whether this is plus or this is minus. So there's a relation between operators, and this comes precisely from the short string sector, right? So it's precisely something that would not be, you wouldn't see in the symmetric orbifold. But in the short string sector, you see that you have a relation between spectral flow, between objects with spectral flow omega and objects with spectral flow omega plus and minus 1. Okay? And this relation allows you to play a game where you relate things with this being even, correlators with this being even, and correlators where you shift one of the omegas in one unit, up or down, and then that becomes the correlator which has the sum of the omegas odd. Okay? And so you can use this to say that if you have a correlator where the sum of the omega I is even, then you can show that there are key relations between this and 6 other correlators, which are where you shift omega 1 plus 1, or omega 2 plus 1, or omega 3 plus 1, omega 3 minus 1, omega 2 minus 1, and omega 1 minus 1. And the point is that these are all odd. So the new, let's say. And since these 6 correlators are all odd, the solution for these 6 correlators is of this form. And then you can use these conditions to relate them, those solutions, to what the solution for the even correlator should be. And this already tells you that it has to be the case that the even correlators were non-zero, right? The even correlators have to be non-zero because they are related with the odd ones in the SL2R model. And you can derive what the solution is. I'm not doing it in detail, but it's done explicitly in the notes. Everything I'm talking about is done explicitly in the notes. And you can find the even parity solutions, which look like this. B by 2, 2, 3, omega 3, omega 3 is some, again, normalization, which again contains the unflowed correlator. And then now you can write the solution in this way. With J3 minus J1 minus J2, J2 minus J1 minus J3, and J1 minus J3 minus J3. Well, now these things take the following form. X, for example, 1, 2 takes the following form. I can write it as 1 minus y2 over a2 of gamma 3 plus minus y3 over a3 of gamma 2 plus y2, y3, so this is y3 over a2 of gamma 3 minus and a3 of gamma plus. There's several ways of writing this thing, but okay. So what does this mean? This means that I can write now this x is instead of depending on either 1 or 3 variables, y, it depends always on 2. The difference between in the parity of these things. And they depend on, they look the same. So if, for example, if I take y3 being 0, they look the same as before, right? So it's basically y minus some a coefficient, right? But now the whole point is that there is no covering map for these even parity solutions. So the things that appear here are the coefficients. So this a2 of gamma 3 plus is the a2 coefficient of the covering map associated to having omega 1, omega 2, and omega 3 when I shift it by 1 unit, because this one exists. Okay? And the same for the rest, right? This is for shifting the 3 down, shifting the 2 up, and so on. These are coefficients of the maps that appear in these correlation functions here. Okay? I get the information from those and I build my correlation. Okay? And now you start seeing that there is something very, very nice. And this is kind of the where I just have a few more comments about the general model. And then we move to the particular case of the tensionless strings. Let me say what the well, first of all, let me say that in general, I don't know of a way of actually for this solution doing the integral over the y variables. The other ones were known integrals in terms of this Proicella hypergeometrics. This one, I don't think it's exactly known how to do it for general values of the omega. The second, so there are some interesting observations. The first one is that so this is more or less clear the structure of the thing, right? Again, it's just I have the explicit correlator in terms of the y variables and the covering map data. So there's a nice comment here is that the xij's they behave like generalized differences. By which I mean that this looks very much like a usual CFT correlator, like what the CFT correlator would look like for unflowed operators if these big x's were little x's, right? So in a usual CFT correlator, if the j's are the weights of my operator, then this is the solution of the global word identities if x12 is just x1 minus x2, right? The usual insertion point. Okay? So these behave in a very similar way, but they are not differences. This x12 is not x1 minus x2. There are some kind of more complicated objects in the sense that they have to do with they depend on the spectral flows and this idea of using the covering map and so on. But they behave very similar to that. And I don't think the structure of why that's the case, of exactly why that happens, is actually well understood. For now, it's just a comment, but it's a very interesting thing, and this structure extends to higher point functions as well. In particular, for 4-point functions. So this one is proven, right? The solution for general omegas for x12 for 3-point functions, be it even or odd or whatever, that's proven to have this form. This was done partly in the paper by Day and Eberhard in 2021, and partly in our paper Puri and Davide in 22. So it's proven that this is the structure that you get, also for the even correlators and what the exact form of the normalization is. The second comment is that this structure of this objects behaving like generalized differences is actually more general than just for 3-point functions. But for 4-point functions, these solutions that I'm going to write here is actually a conjecture. It's also a conjecture by Day and Eberhard, and it has not been proven yet. In 21 again. And the conjecture, if you have V1, V2, V3, V4, now this is going to depend on Y1, Y2, Y3, and all the omegas. And this one depends on the last one depends on the cross ratios. So let's say X, Y, 4, and Z. And you can show that this takes the following form. This takes the form of, well, you can argue, that's what they do in this paper, it's not shown. But the solution to the general recursion relations takes simply the form similar to what I just wrote. So it takes the form of x12 of some x12, which now depends not only on the y1 and y2, which is what it says here, but also on x and z, to the j2 minus j1 minus j3 plus j4, and all the rest of the factors that you would get for the little x's in a usual 4-point function, right? Times, and this is the interesting part, I argue that here in the normalization there was the unfloat 3-point function. Now what happens is that here there is also the unfloat 4-point function, but that's not just a number, it actually depends on the cross ratio. And that gives you V1 with winding 0 at 0, V2 with winding 0 at 1, V3 with winding 0 at infinity, and V4 with winding 0, and this now depends on the cross ratio in Z and the big cross ratio in the big X. Okay, so the big cross ratio, I mean, this is something like X, 1, 2, X, 3, 4, X, 2, 3, X, 1, 4. Okay, so these are not x1 minus x2. These are not the insertion point. There are some mess which has to do with the y variables and the actual cross ratios and so on. But the structure is exactly the same as you would expect. So what this tells is that these factors here basically factorize all the omega dependence up to this function here, which is the usual 4-point function for unfloat states, but evaluated at this generalized cross ratio. Okay, and this, I think, it's a very, very interesting formula, and it has not been proven yet. It has been discussed on a case-by-case basis and argued to be the general solution, but it's actually very hard to prove that this is the case.
And are them polynomials in the y?
Yeah. So the form is still the same as before. So they are still like this, but now you replace these objects by things that actually depend on little x and little z. But the dependence in y is exactly the same. They're always, so x anything is always linear in all y variables that appear here. It can be quadratic in the sense that there's a product of them, but it's linear in each of them. But now there are non-trivial dependencies in x and z. And for high point functions, probably some structure like this would appear, but hasn't been done or argued or anything. And the last comment I want to make is that, again, if we come back to 3-point in general, but we can look at it in 3-point functions, you see that these things depend on y minus a, right? Depend on y. This, for example, here. This depends on this xi depends on y minus a, and it appears here with the power that because j is positive, the power is negative. Okay. And so this tells you, so the factors like x1 to the minus a1, which is I to the minus ai, which is yi minus I minus ai to the minus ji, where this thing here is larger than 1, okay, because j is larger than a half. They tell you that there are these correlators have the correlators have singularities at yi equals ai, which are basically associated with the, in some sense, the existence of the covering map. So you can think of these y variables. So it's a bit more clear in the 4-point function, but I didn't give the. So okay, in the 4-point function, let me say it this way. In the 4-point function, these things become things that depend on little x and little z. Okay, so now this is replaced by something that looks like some p of x, z, some polynomial in x and z. Okay. Yeah. And there are singularities in the correlator when these guys become 0, but the roots of this polynomial. Okay. Okay. And so sorry, when y becomes this kind of thing, and the roots of these polynomials are exactly associated to the existence of covering maps in the higher point function. For 3-point functions, it's a bit more subtle. You can basically, the idea is that you can basically think of these guys here, these y's, as some type of off-shell variable, off-shell coefficient of covering map, right? You have some kind of space of functions which depends on this y, and whenever this y hits the actual values that correspond to the covering map, which are the little a's, then there are singularities in the correlate. That's the sense in which I mean. This will become a bit more precise when we talk about the.
Sorry.
No, carry on.
If the exponent becomes too negative, if 2j is too large, what about the integral over y that gives you back the h dependence? Does it converge if you want to get back the?
It has poles. So the result is a habitometric function which has poles at different values of j and omega and this kind of thing.
Okay.
But you can.
Yeah, you make a deformation. Okay.
Yeah. You just move a bit outside of those.
Okay.
Values and you get. You can compute the residues and so on. Okay.
Okay, so let me ask the question again in a slightly different way.
Yeah.
So at the end of the day, you are calculating some field theory quantities, right? Like I should be able to write everything in terms of the field theory variables. So just with the field theory data that you have, like the OP coefficients and the spectrum of primary operators, how do we interpret this divergence? Because once you bring the covering map, I have to understand it via the worldsheet.
So the same way as so when you had the unflowed correlator, right? Then this C here, this has poles in the J. These poles in the J are associated.
But there are the discrete states.
Yes, they're associated with the. If you think about it in a 4-point function, for example, they're associated with what states are flowing in the channel and so on. These kind of things, it behaves in a sort of similar way.
Okay. Yeah, when you have like different states, when the states go on shell, there is a pole.
Yeah.
And that poles are exactly either the discrete states. J is equal to n.
Yes. Floating, yes. So this is kind of a bit more general than that, but you can think of them as this in some sort of.
Yeah. So from the spectrum point of view, what are these states? Like when do we?
These are the spectrally float states. You're adding all of the poles associated to spectrally float states.
But
So not only when J takes some specific value, but also when H takes the value associated with the spectrally float state. So you're getting formulas that are analytic formulas in H space, in the complex H space, analytic up to isolated poles, and those poles correspond to spectrally float.
Yeah, but those poles should correspond to when J is equals to m plus k omega by 2, m plus n plus k omega by 2.
When H is J plus some natural number or minus,
so yeah, so
k over 2
k over 2. So this pole corresponds to that. That's why I don't see that.
It's ready to.
It's A, right? But A can be.
Yeah, but A has to inform the information of what the different spectral flows are in your correlation function. There are different types of poles in the story. It's not fully precise what I'm saying. I think when we do in the second part, when we do the tensor string, it's going to become more clear what these poles correspond to. So maybe let me wait a bit for that. But I can already answer the other question you had. I said I would answer when I write this, which is you can ask what the Kriging-Samolotchikov is for this object. The Samolotchikov equation is. That's a complicated mess. But what you can show is that if you take that complicated mess and act on this formula, it goes through a bunch of operations on this sector, and then it gives you the Kriging-Samolotchikov equation for this unflowed, the usual one for this unflowed coordinate. That's where it's hidden.
That's how they came to the conjecture. I mean, that's how.
Part of the conjecture is to say I have some recursion relations, which are differential equations in Y, and I have an additional thing, which is the Kriging-Samolotchikov equations, which for these guys is a mess. But when I go through all of them, that gives me the usual one for the unflowed coordinate. Okay. But again, I don't think there is still a completely precise statement of what these things mean. I would say that these things, I like to think about them as associated to the existence of Coring map, but if you want, these are always going to show up as poles in your boundary correlator, and those poles should be matched. Are the poles that you can actually compute by doing just free field theory, for example, using the Coulomb gas formalism or this kind of thing.
Those poles should match with the on-shell states of the boundary theory.
So that's for 2-point functions. For higher point functions, there are more poles which are not exactly, not only they are the poles of the correlation. For example, this thing, for example, has poles not only in some particular value of J1, which is associated with the state, but it has poles where there are some relations between J1, J2, and J3. For example, if J1 plus J2 plus J3 is some integer, I don't know. There are additional poles because you're computing higher point function, not only 2-point function. You're not looking only at the spectrum. So these are the type of extra poles that appear. So these poles are related to combinations of the h's going to either some integer or to some integer times k over 2. Okay, so second part is tensional strings, so maybe that's a good point to stop. Do a break for 10 minutes.
Okay.
Any other questions?
Data from this
Maybe not yet.
really complicated.
Yeah, I mean, once you get used, I mean, it is complicated. For a 3-point function, once you kind of get used to it, it's not that bad. But actually getting the proof for this thing was kind of nice. I've been working on trying to prove this formula for months and months, and I still have no idea how to do it. I have ideas how to do it in some cases and so on, and in some subfamilies of correlators.
But I mean, these are like stupid questions. So there is this quantity z, right?
Yeah.
No, so
About your question, Mariana, sorry. Again, as for the actual deduction of these correlators and so on, I mean, I don't have time to do everything. So I wanted to give as much detail as possible on the worldsheet theory, and that in particular has the consequence that I don't have a lot of time to explain the symmetric orbifold, which is a whole other story. But the key thing you need to know is what I was saying at the beginning, that you have a number of copies of a given theory, and you're gauging the permutation symmetry between them. That's the symmetric orbifold. If the original theory is a CFT, then the symmetric orbifold is a CFT. And the way you compute the correlates, you have twisted sectors because you have twisted boundary conditions relating the different theories between them. And the way you go and compute correlators, for example, I started with Lunin and Matur in 2000, is to, whenever you have twisted operators, you go to some covering space where you trade different copies of the theory for different sectors of a wider space, let's say. So for example, if you have just a sigma 2, a twist operator, which tells you that when you go one around Z on the field in the copy 1, then that gives you the field at the same point but in the copy 2, right? So I should use X because X is the coordinate of the boundary. And the same in the other way, right? X1 goes to 2 and 2 goes to 1. Then instead of having two functions which have twisted boundary conditions, you can go to a space which, instead of being, say, a circle of length r, is a single of length 2r. That would be the variable z, so the covering space, where if you are in the first half of the circle, you call the function x1, and if you're in the second half of the circle, you call the function x2, but it's a single valued function now. So going to the covering space, that's the job of trivializing the boundary conditions, twisted boundary conditions. And then computing correlators there is just the usual computation of correlators of a normal CFT without twisting anything. But there's a price you have to pay for that, which is, again, you're changing from a variable x to a variable z, such that x is gamma minus 1. Okay, you have a covering map, and at each xi, at each insertion, you want to have this. And you pay a price, because whenever you change the space you're working on in a CFT, you have a conformal anomaly. So you have to add something. You have to multiply by some factor. It's something you need to compute. And the conformal anomaly, you compute it in terms of some. So in the original papers, you can think about it as an extra contribution from a Liouville field, whatever, but you have something else to compute. So the final computation of the correlator is this conformal anomaly thing times the correlator in the covering space. And this is the kind of thing we get. And whenever you can show that whenever there is no covering space for that correlator, the correlation function is just zero. That's basically all you need to know to make sense of what I'm trying to say. Anyway, there is, by now, as I was saying, I don't get to cover everything. There are many things extra in the lecture notes. In particular, there's an appendix on symmetric orbifolds with all of the relevant things needed to. It's not complete, of course, but it's all I need to compare with the worldsheet theory. Okay. So now we get to the meat of or some of the most important recent developments, which are based on what happened. So this is again an Everhard, Gabardier, and Gopakumar result. Well, they've been working on this from 2018 to probably 22 or even 23. So there are other authors here like Knighton, Andrea Day, and many others. I have worked personally on the generic model, but not on the one in particular. But let me make a discussion. So I need to answer two questions, right? First of all is why do we call it featureless? Everything okay? And why at k equals 3? Okay? And let me actually make a disclaimer here of the method I'm going to use. Which is, first of all, the actual tensionless string on the statement is that AdS3 cross S3, the result from this vector is that AdS3 cross S3 cross C4, so strings on AdS3 cross S3 cross C4 at the tensionless point, which is defined as the case where the number of brains is 1, the number of 5 brains in the source is just 1, so the minimal possible number is exactly dual to the symmetric orbifold on C4, where if you want, here there's also an N1 number, which is the number of string sources, and here there's an N1. Here.
It's not a string 0.
So, okay, so G-string N1 large means G-string going to 0, N1 much larger than N5 means G-string going to 0. Actually, I'm going over the detail here that as we argued that at some point in the first lecture, this is actually not something which is a conserved number because you have because you can emit strings and absorb strings. So you really this is not fixed. And so what's actually true is that the grand canonical model here is dual to the grand canonical model here, where you sum over all possible values of N1. But at the level of the correlation functions and of what I'm going to say, you can just imagine that you have a fixed N1 here and a fixed N1 here. So the disclaimer is the following. So this is a supersymmetric, right, model. And what happens is that when you build the supersymmetric model, which is not the thing that I've been writing, you can write n equals 1 super Wasumino-Witten model, which is on SL2 R plus SU2, which is the S3 factor plus the T4, which is U1 to 4. And the levels that you put in the supersymmetric model are exactly N5 in both cases, because the N5 sets the size of the AdS3 and the size of the S3. But actually, when you take the supersymmetric model on SL2R and the supersymmetric model in SU2, you can decompose it as a bosonic model with a level k being N5 plus 2 plus fermions, 3 fermions. And similarly, this one you can decompose as a bosonic SU2 at level k prime, let's say, equals N5 minus 2 plus 3 fermions. Okay?
You're writing very small for something very important.
But it's right. It's right.
Okay, let me write it here.
Unread, yes.
So the n equals 1 model on SL2R at level N5 is exactly equivalent to the bosonic SL2R model at level k equals N5 plus 2 plus free fermions. 3 free fermions. And the n equals 1 SU2 Witten model at level n5. You can write similarly, you can decompose as a bosonic SU2 at level k prime equals n5 minus 2, thus 3 free fermions. This is just a fact about supersymmetric Witten models. You can just always do this decomposition. But the key point here is that at n5 equals 1, you get that the SU2 level becomes minus 1. Right? Because I shift this by 2 units. And for the usual compact bosonic Witten models to be unitary, you need positive values for the level. Okay, so this tells you that the usual way you write this, so the RNS formalism, which is what I'm using here, breaks down. At n5 equals 1. And you should use the hybrid formalism where you stop insisting on separating this in this way and you just work with the full supersymmetric PSU 1,1/2 model at level 1. Fine. This is a fact of life. At n5 equals 1, you cannot use the RNS formalism I think described. But the comment here, the interesting comment is that the problem is really not in the AdS sector. Right? The problem is in the SU2 sector. That's where things become complicated. So, since the problem is in the SU2 sector, many of the interesting features are there in the SL2R model at k equals 3. K equals 3 because here I have n5 equals 1 plus 2. Okay? What I did in the notes and what I'm going to do here, there are many references on the how to use the hybrid formalism here. I want to keep using the same language because it already contains most of the information that we need. And if you want more details about this hybrid thing, you can ask Jakub, for example, who knows a lot about it. I'm not an expert on this, but again, I think most of the interesting features at this point, the attention point, you can already see in this model. Right? So that's what I'm going to use. I am going to use just the SL2R model at k equals 3. Okay. Now let me go. That's why this answers the question of why k equals 3. Let me answer the question of why tensionless. Of what happens at this point. Okay. Any questions on this before I start with this, with the actual model? No? Okay. So let me remind you what first of all, what the physical state conditions are. For strings in, again, the bosonic strings in AdS3 cross some internal manifold at k equals 3. Okay? The physical state conditions we already wrote at some point. These are just the Virasoro constraints. And they look like this. There's one on the holomorphic side and one on the anti-holomorphic side. So this is the usual weight. This is minus omega h plus k over 4 omega squared plus the internal weight plus the descendance level minus 1 has to be 0. And then I have the same thing in the anti-holomorphic section, where the only thing that changes is that I can have a different h bar and a different internal weight. And for once in the course, I'm not going to stay on scalar operators, and I'm not going to stay on primary operators. So I'm including the difference between h and h bar and the difference between the non-zero n and n bar, right? So this whole thing is just a weight on AdS that depends on the K, M, and omega. And then, well, and this is what you would call the internal weight. These are the Virasoro descendants. And if you just subtract these two, you get the level matching condition, which is just omega h minus h bar to be n bar minus n. Because that's the only difference between holomorphic and anti-holomorphic. And now the question is, how do you check where there are higher spin states which are actually massless? And you have to remember what the formula for the mass in AdS3 is. And the formula for the mass in AdS3 you can write in terms of the space-time weight, right? As follows. So let me write it like this. So you can write it as so this is the usual formula. So this is the conformal dimension in the space-time theory, the full conformal dimension. This is a spin minus 2, and the conformal dimension minus the spin, where in our usual language these are defined as h plus h bar, and the spin is defined as the absolute value of h minus h bar. Okay? So again, this is the usual type of formula for masses in AdS, and this is the relation with the worldsheet variable, with the spin, right? And you immediately see that massless states they happen when this factor here cancels. Right? So I have zero mass, well, any of the two can cancel, but if this cancels, I have a massless state. Okay? And if it cancels non-trivially, so if this is non-zero and this is non-zero, then I have a massless state with spin L. Right? Okay? And this condition, massless states of spin L, happen when this is 0, and when using these formulas, you show that h bar must be 0 and L must be h, for example. Or h must be 0 and L not this H bar. Yeah, these are the only two options. Okay, fine. But this is a way of obtaining, this is what massless states of generic spins should satisfy. Okay, so the whole question about having higher spin massless states, if there are things that satisfy this and the physical state conditions at the same time. Okay? If I find solutions to both of these things, then I have massless higher spin states. Where if I find a tower of solutions with arbitrarily large h, integer h, then I have a tower of massless higher spin states, which is what's going to happen here. So again, I'm calling it tensionless limit, not because the actual tension in the sense of alpha prime of the tensions of string in flat space, I'm taking that to infinity, so the 1 over alpha prime is taking to 0, but in the sense of this is the point where I get a tower of massless higher spin states.
Nico, I have a question.
Yeah.
This mass formula that you have written,
Yeah.
that I think we trust in the supergravity limit, not in the stringy limit.
Yeah, you can do the same. You can.
No. How do you do that? There is no way you can derive that thing in string theory limit. I think it's a motivation that you are trying to present, but it's definitely.
No, but you can. What you can show is that you can do it at the exact level in the sense that you can take. You can show that at this point there are holomorphic operators of arbitrary in the boundary theory. From the worldsheet, you can show that there are holomorphic currents of arbitrary higher spin which are conserved, and that you can do at the level of correlation function.
Yes, maybe that you can show. But this is like more like a semi-classical, not a semi-classical, like a.
No, it's by far not semi-classical because I'm going to do that k equals 3.
Yeah, it's not semi-classical. Like it's classical, but it's not.
It's geometric, but it's not classical. If you want. I mean, it's the geometry.
Because it's gravity is classical. That's not the point. My point is that you are following some formula which is valid at supergravity approximation, and you are using it in the stringy limit. But I think the other argument that you gave, I think that's much more.
Yeah, you can do it at the level of the actual conservation conditions. And exactly, I agree.
But even if it fails, you cannot conclude that. Even if it happens in this argument, you cannot conclude that there must be massless high spin currents. Other currents.
I have to think about it exactly. I'm not exactly sure that you can't argue that whether this is enough or not.
Yeah, because this is a supergravity. This is by solving Klein-Gordon equation you obtain these things.
Yeah. But you can define, I mean, just from here you can define what you can do the usual thing, you can identify what you call momentum and you can define what p squared is and so on, just from the worldsheet point of view, and then try to argue that p squared is going to give you 0 or not.
The p squared, you mean a squared? P, I mean the momentum.
P, the space-time momentum of some state. So usually what you do in flat space is you take the space-time momentum, which you can define from the worldsheet, and you compute p squared, and that gives you 1 over alpha prime times stuff on massless state, and you get the massless state and the massive state in string theory and so on. Here you can do the same. You probably do the same.
Okay. And this is this paper of Gebardiel and Frisal, right, that you were presenting.
Yes.
Yeah. I think that's a very crude argument, like to get means that there can exist a spin tower.
2017, I think.
Yeah, something like
that. Yes, but again, you can do it at the level of the
I think it's Gopakumar, not Gebardiel.
Very bold.
I think it's Gopakumar.
Okay, I'm sorry. I apologize. I don't remember exactly.
Right, yeah.
Oh, sorry, no.
We can.
Yeah. So you have a tower on the left, a tower on the right, and then the graviton. And that's.
I'm going to show the solution now.
Okay.
We can discuss a bit more details later. I think the argument is a bit more precise than what you're saying, but I have to think about how.
Okay, I mean, I don't know. I mean, I always think that paper to be like to get an idea that there may exist something like that, and then in the supergroup formalism they can make the statement much more precise.
Yeah, I mean, of course, you can't do it at the exact level you're doing with the full super.
Yeah, this is like how to develop intuitions, maybe.
Anyway, you don't need supergroup here because in principle you can use just RNS formalism, not in the supersymmetric case. But this is true in the bosonic case.
Yeah, but in the bosonic case you also have the discrete states. I don't think the discrete states go away.
The discrete states are there, but you can show that at k equals 3 there are higher spin conserved cores.
Yeah, on top of the discrete states.
On top of everything else, yes. I'm not saying that in the bosonic model that's the dual of the symmetric oriflow. I'm just saying you can show that you have higher spin states.
Yeah.
Master states. Okay. Fine. So how do I find solutions? So first of all, I have the universal solution. Which are just, as Mariana was asking, the graviton, the big field, and the dilaton, right? Again, I'm in bosonic string theory here, so I don't have the Ramon sector. Or I just have these three. And these solutions correspond to the simple way of solving this, which is to take j equals 1, m equals n bar equals 1. So the usual thing that is they are all at level 1 in the sentence. The internal part being trivial, and the spectral flow being 0 as well, right? This is a very, I call it universal because it doesn't really depend on what else you get on the internal sector or whatever. You just set this to 0. So this again, so this would be the state that corresponds to the direction to the gravitons and the B field polarized in the AdS direction, right? But these are the solutions to all of this that I just said, right? But these are spin 0, 1, and 2, right? The graviton, the B field, and the theta. So it appears that this solves all conditions. Okay.
You can do the same with internal, right?
Yeah, I can do the same with internal, and I get the metric in the other part of it. Yeah. So here, let's say I here. Okay. Then you can just show, and I'm not going to do it here, that there are no other solutions. So note that here I'm taking j to be 1, right? So j to be 1 means I am in a discrete sector of the theory, right? It's a real value. It's a real value for j, which is not just 1/2. And by universal, I also mean that this works for any value of k. And I'm not saying anything about k. So for all of this, k larger, which anyway is the unitarity law. There are no other solutions in the short string sector. Even for omega larger than 3. So there are just no solutions. You can show very explicitly that you cannot solve all of these conditions at the same time in the short string sector.
So if you did from the three perifermions, there are, I mean, you have solutions with partners.
Yeah, of course. Because here I'm doing bosonic theory. If I do it in the supersymmetric theory, yeah, you also get the Ramon sector and so on. But they all look like this. They all have, in particular, they all have j equals 1 and for the AdS3 sector, they all have j equals 1 and 0 spectral flow. They're all particle sectors. There are no more solutions in the short string sector, but what you do get is some solutions in the long string sector. So for concreteness, I'm going to take, you remember that I had to take, if I want master state, I take either h bar or h to be 0. Okay? So here, just for simplicity, I'm going to do it for h bar equals 0. And I want to show that this is independent of the details of the internal sector, so I also take h internal, h bar internal being 0. And I'm also going to take the descendants level on the anti-holomorphic sector to be 0. Okay? For this family of states, then from level matching, I just get that omega times h has to be n. I think I have a typo here. Okay, fine.
Long string with h. Yeah, sorry. That's a.
I may be mixing n and n bar. Oh, no, that's okay. That's okay. No, that's okay. Okay? Now, I am in a long string sector, right? So, J has to be 1/2 plus IS, where S is real. And this tells me that minus J times J minus 1 is 1/4 plus S squared. Okay? If you just plug this in the conditions, so by doing this, I already solved level matching, right? So I only have to look at one of the Virasoro conditions. And by having this, I'm already having master states. So I look at the remaining Virasoro condition, which now looks like this. So this is what I need to solve. The first thing you notice is that for k larger than 2, right? The only possibility for this to be positive, you cannot go very high in omega, right? Omega has to be small enough because there's a minus sign here. And this guy is positive. So you show that the only solution must have h equals, or omega equals 1. So the only possibility of the right-hand side of this equation being 1.
So now you're doing this for any k.
Yeah, and I'm going to show that k equals 3 is the only case where you get solution. Okay, so you do it for, you only look at omega equals 1. For omega equals 1, I can just write this. I can just rewrite this equation as s squared equals like this as 1/4 plus s squared being k minus 2 times 4 minus k 1/4. Right? I just set omega equals 1 and take the 4 outside of here. Right? And then you see that this thing here is an inverted parabola, right? With roots at k equals 2 and k equals 4, centered at k equals 3. Okay? So you can show that this guy here takes the form of something like this, it has that k, so this is k equals 2, I have a 0, k equals 4, I have a 0, and then at k this is inverted at center at k equals 3, right? So it all the tallest possible value is at k equals 3, and at k equals 3, this is 1, this is 1, and this is 1/4, so I get just 1/4, right? So you get something like this. And the only possible solution to the system is the only solution is that s equals 0 and k equals 3.
You want to restrict yourselves to integer k, but here k may not be an integer because there is no SU2.
Yeah.
It can be anything.
But still, any value that's not 3 gives me something that's smaller than 1/4. This is
I see. So if k is okay, so for k between 2 and 3 and 2 and 4, this function is positive, but you want it to be.
I want it to be 1/4 or more. 1/4 or more.
Require.
The only solution is k equals 3.
So basically, yeah, I see.
Okay. At this point, I have a whole tower of massless higher spin states. Why? Because I can just come here and say I take the guy at descendance level 1, and I had omega equals 1, right? So this is not here. I take the guy at descendance level 1, it gives me weight 1, which is the spin, so I have spin 1, and n equals 2 gives me spin 2, n equals 3, spin 3, n equals 4, spin 4, etc. Okay? So I have a whole tower in my spectrum of massless higher spin states.
But that's when you find many other quantities, right? Like omega equals 1, you get h equals.
I didn't find anything. I'm just trying to find solutions which are massless higher spin states.
Yeah, but what I'm saying is that for other values of k,
There's just no solution.
but you didn't prove that statement, I think. Yeah.
For the short string sector, no. For the long string, I just did.
For the long strings, you restricted yourself to h internal equals to h bar equals to n bar, right? I mean,
Yeah, because I want to say that I have a universal that whatever the internal sector is, I have this solution. You can actually show just using that these guys have to be positive because the internal sector is compact. You can show that there are no extra solutions. Okay, so here there exists an infinite tower of massless higher spin states with spin L spacetime being M being H. Okay?
for omega equals 0. So if
The only solutions that omega equals 0 are this one.
so I take the equation inside the red box, set omega equal to 0. So I have 1/4 plus.
I don't have long strings at omega equals 0. Those are Tachier.
But you are doing bosonic strings. You are not doing.
That's it again. So in the unflowed spectrum, there are no continuous states. That's what I showed.
No, that's you said that I don't like tachyons, so we just exclude it from the spectrum. But like in bosonic strings, there are tachyons, right? You don't exclude it from the spectrum. You said that the way to see it, I will say that in superstrings they will go away.
But anyway, they would be negative mass, not zero mass. Okay, let me say it this way. Whatever I did here doesn't hold for omega equals 0 the way I wrote it, because for omega equals 0, I cannot solve this thing for arbitrary n. Okay. You can show that there are no other states.
Yeah. Mass squared will be 0. Yeah.
Of course, I'm way behind schedule, so I would like to say as much as possible about the tension string because it's kind of one of the most interesting things out there, even in this language. So let me try to say what happens more precise. So now I'm going to, for the scalar spectrum, you can show, and I'm going to only give a heuristic argument. So this is important. Any questions here?
The discrete spectrum, there
That one I didn't show it, but there are no solutions.
are no solutions for omega greater than 0. For omega equal to 0, there are discrete solutions.
The usual ones, the supergravity field.
The usual supergravity. Well, I mean, you mean just the metric dilaton and the B field. That's all. That's the.
In this Bosonic case, yes. In the supersymmetric case. Okay, so far so good. It's kind of nice that this really only happens at k equals 3, not even k smaller than 3, which you could also think. Which is also kind of, the space is less than string size, but still there's no higher spin. So on the scalar spectrum, I'm going to import something from, this is the only place where I need to use something from the hybrid supersymmetric model, which is that you can show using the representation theory of PSU 1,1/2 at level 1 that 1, the short string in the supersymmetric model, the short strings drop out from the spectrum, and the long strings can only have exactly j equals 1/2, so s equals 0. Okay. So what I'm going to say is not precise. So precise, you can do it in the supersymmetric model. In the bosonic model, there's kind of a heuristic way to say it. So at k equals 3, the ADF space is string size. Okay, and since it's so small, first of all, this condition is basically saying that there's just no space for bound states in your. It's just no physical space because you want to have short strings which are actually string size, not only particles, just actually string size. They're gonna have some generic size, and then there's just no space for bound states.
Well, this cannot be like the full thing, right?
This
As
is
you
just-
just mentioned, that
this is just a
substringy one, there are all in the substringy case, k less than 1 or k less than 3, whatever. There are the discrete states. There are discrete states.
Well, it's not in the normalized perspective. I mean, it's kind of what if.
I mean, there are discrete states. That's what I said. Yeah, there are discrete states. Some of the vacuum is not normalizable. That's what you're saying is right.
Yeah.
Discrete states.
Yeah, I know. But the vacuum, they are there in the vacuum is not. I mean, substring is more subtle than that. And again, I'm just giving a heuristic argument for why you can think that this is the case. It's not the precise argument. Precise argument, you can show it from representation theory of this guy here. I'm not doing it because I don't want to get into the hybrid format. So just take this between quotes. One way of thinking the same is that normally, so for example, for chiral, so you always have this bound, right? This bound on the short string sector, right? But for k equals 3, this is exactly 1. Okay? And for, say, for example, chiral operator in the supersymmetric theory, you always have this condition that the spin in SL has to be the spin in SU. So the spin, this one minus 1 has to be the spin in SU in the SU2 section. Right? So when you want to build the chiral operators in the supersymmetric theory for general K, you always get this sort of condition, a relation between the spin of the short strings in SL2 and the spin in SU2. But you have this minus 1 here. So if J is smaller than 1, then this gives you a spin in SU2 which is smaller than 0. And again, that kind of has to drop out of the spectrum. These are just heuristic ideas to say that it's reasonable to think that the short strings drop out of the spectrum. Yeah.
What does it mean in terms of the metric? If it can be that one?
You can, it means because, so the point here, this point here is at exactly 1/2 is the point where there is kind of a degeneration, where the short strings and the long strings coincide.
It's not there.
And you can, what happens is that you can, these states that were there for J equals 1, you can re-see them as long strings by using this, by using spectral flow. Because you can think about a long string which has J equals 1/2, and then you add 1 unit of spectral flow, right? And you get the state, the equivalent of the states with that I wrote there. Again, this is particular for K equals 1. It's also discussed in the Hall paper. And the long strings can only have S equals 0, and again, the heuristic here is that S is basically the radial momentum. And because these long strings are large, the idea is that, and the space is actually very small, that they cannot really move inside the space. They have to stay near the boundary. So S equals 0 means that long strings stay near the AdS3 boundary. Again, just heuristic, but I think it's a nice intuition to have. And so the question is, what does this imply in general for the spectrum and for the correlate? So again, for the scalar spectrum, I'm just going to write the holomorphic physical state condition, because the anti-holomorphic is going to be the same. So I get what I wrote there, which is 0 equals minus J minus 1 over J minus 2 minus omega H plus J over 4 omega squared minus, I'm going to take the internal sector to be trivial, or no, not necessarily. Minus 1, and I'm going to look at the primary sector, or Virasoro primary. So I don't write the n here. Okay? And the point is that in the long string sector, which is all I have at K equals 3, or if I, in the bosonic, that's true for the symmetric model, if I focus on the bosonic model, I can say I focus on the long string sector. And because for long strings, for the continuous representation, there was no relation between J and M, right? And M is basically this H here. I can just use this condition and solve for H, because H can take any value. And so I can say that the solution takes the following form. So this is a general statement. This is true for any j and any k in the long string sector. Okay, where I can actually use this to solve for h. But if I see that k equals 3 and restrict to j equals 1/2, which is the only thing that survives in the supersymmetric model, okay, I get something very nice. Because if you put here j equals 1/2 and k equals 3, what you get is that the spectrum, the holomorphic part of the spectrum, looks like 3/4 omega squared minus 1 omega plus h in over omega.
I'm confused how these are scalars.
Because I'm doing the same, because scalar means h being the same as h bar. So I'm not writing the anti-harmonic sector, but I'm saying it's the same.
Scalar.
It's a space-time scalar. Literally. So as the SL2R spin after spectral flow, which is h, if you scalar field means you have the same spin on the left and on the right. The SL2R left and the SL2R right. But because you remember that I wrote that L spacetime was the absolute value of this. So scalars are just h equals h bar. Before I didn't want to look at scalars, I wanted to look at higher spin. Now I'm just looking at scalar field.
And you are back to bosonic strings, right?
Yes. So this blackboard here, this statement was just to motivate why it's interesting to look at only j equals 1/2. But what happens at j equals 1/2? Which is I'm going to, in the supersymmetric model, the only thing that survives are long strings at j equals 1/2. But again, if I look at those states in the bosonic model, most of what's interesting in the tensional string, in the actual tensional string, is already there. And so this you can compare with the spectrum of a putative holographic CFT, which would be the symmetric orbifold of n1 copies of what do I want to say? Yeah, of some manifold which has the central charge, also some original, some seed CFT which has a central charge, which has some central charge. Okay, and this, what you get for the spectrum is exactly the following: C over 24, C seed over 24 times this plus H seed over omega.
So these are the marginal deformations of the.
No, I'm not saying that they have weight 1. This is just a full spectrum of scalar operators, primary scalar operators in a symmetric orbifold field. A marginal would be to have h equals 1, h bar equals 1. And so you see that this formula is exactly this formula. Well, again, omega here is the spectral flow, and omega here is the twisted sector, right? And this actually is the weight, the weight of the twist operators only, and this is what you then use to dress them with the actual excitations of the sphere. And so you see that this is the same formula for CC equals 18. Okay? But 18 is not just some random number. 18 is in this case 6 times 3, which is 6 times k. At k equals 3. Okay? So this is telling you, remember that we were saying that in the symmetric orbifold comparison, we had the C of spacetime being the C of the seed theory times the number of copies, let's say n1, and this had to be 6 times k, or in the supersymmetric model, this is 6 times n5. Okay? In the bosonic model, that this happens at k equals 3, and this is, you get exactly the formula for the scalar spectrum, and you can do it for other non-scalar operators, but for the spectrum of asymmetric orbifold for all the states which have j equals 1/2, and arbitrary spectral flow and arbitrary h ins which solve this thing. Okay? The spectrum is the same.
You are not claiming that k equals 3, the boundary theory is a symmetric product. Because of the omega 0 discrete states that do not fit in the structure.
It's a bit subtle. I'm not saying that it's a symmetric orbifold of D4.
It's not a symmetric orbifold. Because the discrete states do not fit in the structure.
Yeah, it's a bit subtle. So there are, again, a lot of interesting things that happen only in the bosonic model at k equals 3, but I'm not claiming that it's directly a symmetric orbifold. I'm just trying to write what happens in the supersymmetric model in the language that we were using throughout the course.
Yeah. But if you just restrict yourself to the long string sector, I think you can make this statement for any value of k. That just the long strings they form.
Yeah.
So that's what you are saying, that that k equals 1 is consistent with k equals.
It's not exactly true. I mean, it's true, but if you do long string sector, but for general j, you're going to have another contribution here, which is going to tell you that it's not only, so it's true that it's symmetric orbifold, but it's not a symmetric orbifold. The way you get the 6k is that you have to add here, you have to add a non-compact scalar with some background.
Yeah, you didn't specify what mseed is. You are not saying
mseed
has some Liouville.
It's always true. It will always be true that there's going to be some M seed in the long string sector for general k that does this thing, and they give you central charge 6k. But in the supersymmetric model, you have to restrict to j equals 1/2, and if you restrict to j equals 1/2, this is all there is.
Yeah, that's a supersymmetric.
Yeah. But again, I didn't want to spend one more lecture just doing all the definitions of the hybrid thing and writing everything like that. And I think it's nice to see it this way. And then there are a lot of references actually going through the Jakob's papers in particular, going through the hybrid model. I think this is a nice way to see it. By the way. Okay.
Just one more comment. I think this k equals to 1 is very specific to SU2.
Yeah.
Right? Like even if you study AdS3, S3, S3, S1 at k equals 1, or like whatever the tensionless limit in that case, it's not a symmetric product. That has been proved.
No, it is. Also, there is one limit which is a symmetric, which is supposed to be a symmetric orbifold, which is when you take the level on one of the S3s.
It's not. That's what I think is proved by the paper of Porati and Chris Hall and.
If you go into the detail, I know there is a paper by Eberhard, I think I'm sure, claiming that when you take one of the N5s, one of the levels on the SE2 to go to 1, you get a symmetric orbifold. Instead of D4, you get a symmetric orbifold of S3 crosses 1.
This
if that's expected or not,
the paper they disagree with that statement.
I don't have any useful comment on that. I mean, I did look at some data at some point. I think some things work, but I don't know if the full thing is true.
Yeah, I mean, if you look at the long strings, it must work. I mean, that's a 20-year-old statement.
Yeah. Okay, so let me, in the last 5 minutes, just make a statement about what happens with correlation functions, and then we try the details next time. You remember that we had for 3-point functions a solution which looked like this, right? For the odd 3-point function, minus 2 to the 1, x2 minus 2 to the 3, x3 minus 2 to the 3, x1 to the 3, k over 2 minus k1 minus 2 minus k2. Right? This was the 3-point function. Vj1, omega 1, y1, etc. Right? So you look at this thing and you ask what happens if you restrict to k equals 3 and ji all being 1/2. Okay, which is the same I was doing for the spectrum. If you do this, then you see that this factor drops out. Because I have 3 over 2 minus 1/2 minus 1/2 minus 1/2. And all of these things become x1 to the minus 1, x2 to the minus 1, x3 to the minus 1. Okay, well, remember that x1 was y1 minus a1. Okay, so this is one possible solution. But what actually happens is that if you look at the actual differential equation, and you get a clue from the fact that you have a minus 1 here, but the weight is exactly minus 1 in terms of this x variable. So at k equals 3 and j equals 1/2, there is actually the differential equation in the y variable actually admits a new solution. Which is Vj1 omega b 1/2 y1 b 1/2 y2 b 1/2 y3. And the new solution that you get is just that there is an actual distributional solution where you trade this x1 to the minus 1 for Dirac delta function. So you can show that this solves the same differential equation. This type of distributional solution is not there for other values of j or other values of k. Well, actually, if you stay at it, they are somewhere there if you have some precise relation between all of the j's involved and all of the value of k, but in particular not generically, and they are there for k equals 3 and j equals 1/2. You see that this is more or less it's kind of simple to see that it should be the same solution, because as under the action of differential operators, these things behave exactly in the same way as this, as 1 over this. Right? When you act with differential operators, they behave exactly the same. So they had to be, if you admit distributional solutions, there's going to be one of these 4. Which is not true. The mass dimension, which mass?
Yeah, I mean,
The j, you mean?
well, I mean, the j's, yeah. But
The
j
j is 1/2. It's fixed.
Okay, so let me ask you this question in a different way. What is the dimension of v in the y variable? Because it's some integral transform of vx.
for j equals 1/2, if you want, it's weight 1.
Okay.
If you want to call it weight, but there's no, it's not a variable for which you have the usual word identity. But okay, if you want to think about it in terms of power expansion in y, yes, it has weight. And 1 in the sense of this minus 1. And this is telling you that where the general correlators used to have singularities, right, which is when these variables y coincide with the numbers a, the coefficients of the covering of data. What happens in this case, and you can show that in the supersymmetric model, this is actually the solution that you need. It's not this one, but this one. What happens is that not only now I don't have divergences there, so I integrate in y and this gives me a finite thing, but these are the only places where I have a contribution. Okay, so there's what people usually call localization of worldsheet correlators on the singularities of the k larger or different from 3 correlators.
That's why there is no simple relation between AI and the weight.
AI is the combinatorial thing defined in terms of the omega.
So if you said Y to AI,
no, in principle there's no clear, as I was saying, there are things when you can understand why they are related in this way. I like to think about why that kind of, because so let me just kind of say that this is more or less the end, and then we can discuss the questions, and I say the more general statement at the end, on Monday, the last lecture. But the idea that I like, the way I like to think about it is that, so the A's, right, the covering map, and in particular the covering map data and these A's, are not properties of one operator, right? They are properties of the full correlator you're trying to compute. They involve all of the omegas that are there. But the Y is some label on each single operator. It doesn't depend on what correlator you're looking at. So in a sense, I like to think of these Y's as kind of off-shell versions of these guys. In the sense that when you, in tensional string in particular, that's the case. When you look at the correlator, it's only going to be, it's some label in your complicated representation theory, but you're only going to have actual non-zero correlators when it takes the value it should take in a given correlator to give you a covering map. There are different kind of, you can say that in a more or less sophisticated way. I don't think the actual general statement is precisely understood. But what is understood is that this property, this thing happens here for the 3-point functions. And moreover, what happens is that in the tensional string case, you can show that this localization property on the covering maps actually solves the recursion relations for all higher point functions, not only for 3-point functions. Which again is by far a huge amount of new information compared to the general K case. These kind of things, these kind of properties happen in all of the correlators of the theory, and you can actually show it. And the reason for why you can show it, if you want, is that, and that's what I'm going to try to do next time, partly, is that I was saying that you're only looking at long strings which are at the boundary, right? They are sitting at the boundary and there's no radial momentum. If they are sitting at the boundary, then, as if you remember about the discussion of the Wakimoto variables, you can think that at the boundary the interaction term is really zero and the free field description is really accurate. And that's why at k equals 1, so in the supersymmetric model in particular, then k equals 3, in the supersymmetric model at n5 equals 1, you go to a situation where the CSU1,1/2 model has just a free field realization, which is exact. It's not perturbative. And because of that, you can use properties such that in our language that gamma and beta are actually holomorphic, and then you can use that to show that the little gamma is going to behave as the big gamma in the correlator, which is what I was saying last time. The amount of field gamma is going to be in a correlator, is going to be related to the covering map for that correlator. And that kind of tells you that if that covering map doesn't exist, then the correlator doesn't make sense. And then you can argue that correlators are non-zero only if the covering map exists. And not only, and it also helps you do everything. It helps you integrate over the worldsheet variables and so on, and you can show that explicitly that the correlators are, once you integrate over the worldsheet insertions, are the correlators of the symmetry copy. Exactly.
The sum of omegas is all.
Yeah. So in the tensionless limit, all of the even ones go to zero. Because again, this property relating omega to omega plus 1, right, that we had to derive the even correlators, that comes from the short string sector, from the identifications in the short string sector. Here's no short string sector, so there's no reason why, if the odd ones are non-zero, the even one has to be non-zero.
The worldsheet itself is the boundary.
The worldsheet is the covering space of the boundary, but the worldsheet is sitting on top of the boundary, the worldsheet of this string, this strong string.
There is no bar in some sense.
Exactly. Yeah. I'll be a bit more precise about all that. I wanted to do it today, but there was no time, so I'll be a bit more precise in the first half of the last lecture, or what I just said. And there's a very nice story about little gamma behaving as the covering map and so on, which is subtle and very nice. But as a slogan, if you want, what you get is that all worldsheet correlators localize on the points in whatever moduli space you have, on the points where the covering map actually exists. And that helps you solve everything. And it also works for higher genus, which I didn't do here. It's also true. You can get covering spaces of higher genus, genera, and find those functions more or less explicitly and argue that those are going to be the correlators on the worldsheet and blah blah. So at k equals 3, what happens, as Jacob was telling us last time, is that really literally the worldsheet that you're looking at is the covering space of the Z is the coordinate in the covering space of the boundary field for a given correlate. That's it. Questions?
Is there a position space analog of this correlator? Because it's simple enough.
Yeah.
What does it look like?
And so, yeah. So in position space, you just have to integrate this, right?
Yes.
So here, I mean, the variable dx are just 0, 1, and infinity, right? So position space is just a number.
Yes. Exactly.
And if you remember the relation between the VH, I don't write the J here because J is always 1/2 now, so I don't care. So the VH omega of x, z, and the Vx, y, z omega is an integral over y, and then some power of y, which is j minus k over plus k over 2 omega minus 8 minus 1. Okay, so in this case, j is 1/2 and k is 3. Yeah. Okay. But this is a delta function, so the integral is trivial. This gives you a power of 8. So you get that VH1, VH2, VH3 at 0, 1, and infinity, 1, 2, 3 is the product So 1 equals 1 to 3 of AI to the 1/2. So 1 plus 3 omega minus H y. Okay. Times some normalization, which was already here. Okay. And this step in particular, the fact that, for example, the fact that the way any correlator in the symmetric orbifold depends in this way on the weight is exactly what you get from the symmetric orbifold.
Yeah. What is that in the AI in the symmetric orbifold?
It's the same combinatorial number, but in terms of the
Combinatorial number.
in terms of in which twisted sector each of these guys live. But the most interesting, I write it next time, but the most interesting thing is that you can extend this to higher point functions. And in higher point functions, you get always these type of things and extra constraints for the other x's and z's, telling you that the map has to exist. But this is kind of simple enough because I can always fix 0, 1, and infinity, but it's a bit more complicated. It works. It works beautifully. Any other question?
Online. Okay, so if not, thanks again.